I don't want people to start missing lectures thinking that they can do it later, you know? So if you don't mind, I just like to do it live, okay? All right, so introduction to reinforced concrete. I usually like to spend a couple of minutes on the title. On any chapter you will see, we'll spend a couple of minutes there. So first of all, it's an introduction. We're gonna start talking about that. And reinforced concrete. So we said, we know what concrete is. Concrete is made out of sand, cement, and aggregate. But when we put rebars in it, or steel, it becomes reinforced. So that's what we're doing here. We are studying reinforced concrete. That means concrete with rebars inside. And we are not studying precast concrete, and we are not studying post-tension concrete or pre-tension concrete. I will explain those as we go, just so you know the difference. But this is mainly cast in place concrete. That means the concrete is brought to the job site and put in the forms, and we build the building that way. Okay, so we will explain the others later on. All right. So you will see for this chapter, we're not gonna punch any numbers, no equations, no numbers, just introduction to concrete. You've probably seen some of it in lab, in the concrete lab and all that, but we're gonna do a much more thorough job for that. All right. So concrete and reinforced concrete. Again, just let me remind you, these PowerPoint presentations are exactly almost a summary of the chapters. So I hope that everyone goes to the chapter and read that, because you will get much more information also in the chapter that's not in the PowerPoint. Okay, but they are in the same order, same format, almost, you know, so please make sure you read the chapter and then get the best out of this.
Oh,
so
Professor?
Concrete, what is concrete? Concrete is a mixture of fine aggregate, meaning sand. And when we say fine aggregate, sand is the beach sand you see, similar to the beach sand. But it's not a beach sand, okay? Because why? Because the beach sand has salt in it, and we cannot use that. So the sand we're talking about, the source of the sand comes from the stones and aggregates. Okay, they grind them so fine to become sand, and you've done sieve analysis in your geotechnical, and then you know so much passing the grade and all that. That's how they classify. But just visually speaking, it's the same, very similar look to the beach sand, but it's not beach sand. Now, somebody could ask, well, can I take the beach sand and wash it and get the salt out of it and use it? Yes. If you can get the salt out of it and use it, then yes, you can do it. But of course, in theory, that's an environmental crime per se. You know, you cannot just take sand off the beach and build in it. Of course, no government will let you do that. But I'm just saying, so you have an understanding of it. All right, so the first ingredient of concrete is the sand, the fine aggregate. Second is the coarse aggregate, which is the small rocks. You know, they're about 3/4 inch diameter, 1/2 inch diameter. Limestone, example limestone. Again, where do we get that from? The mountains. The mountains. And cement, of course, we all know what a cement is. A bag of cement in this country weighs 94 pounds. In other countries in the metric system, they weigh 50 kilograms. Okay, so it's a cement. And then, of course, we have to add water to it and air and admixtures. And then somebody could say, what you're talking about? We'll explain that. So this is that. So some mixes, we add air to it. When we say air, it means air bubbles into the system. And then admixtures, we'll see what the admixtures are in a second. All right, so this is the how we make concrete. Of course, notice that all these are important. Of course, they have to be proportioned the right way. And then there's a graduate class. We don't have it at Long Beach. I don't think any of the schools around us have that. I haven't seen it. But it's called mixed design, concrete mixed design. It talks about nothing but how to prepare mixes You could be working for a ready-mix plant as an engineer, because what happened when we order jobs, when we order concrete for our jobs, we tell them we want a 4,000 psi concrete. We want to use it for the following da, 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 da. And guess what? The engineers on site, they will design that mix for you. They will. What does design mean? Design mean how much sand in pounds you need, how much water in pounds you need, how much coarse aggregate you need, how much cement. And you could design it by pound or by volume, as long as you're consistent. And then you will get the mix. We'll talk much more about that. Okay? So again, the way you mix concrete, it depends. You have to be very careful, and then the proportions of it is going to affect the strength. Of course, very important one, I can tell you, water. The more water you use, the weaker the concrete is going to be. Okay, we'll talk a lot more about that. But this is the first warning I give you, is be careful of adding too much water to the mix. Okay, next is admixtures. So what is this term, admixtures? In summary, the admixtures are really chemicals. Chemicals. You know, in third world countries, they mainly use sand, cement, aggregate, and water. That's it. Most third world countries, that's all they do. So you can have concrete by only these ingredients. But what are the admixtures? Very briefly, and we'll go through that in detail. It's chemicals we added to the mix to achieve certain things we would like to see. Like, for example, we want to make the concrete more workable, because the more workable it is, the easier on the workers. If it's too hard, it's not easy on them. So there's a chemical you can add to it, and then it make it workable without losing its strength. You do a manhole in the middle of the street, and you have to close the street by tomorrow morning. So you need your concrete to set quick and harden quick. So you add some chemicals to it. So these are the admixtures, all right? And then we're going to go through them. So admixtures are materials other than cement. See that? They're not cement, they're other than cement. Aggregates or water, there's something different than all these, that are added to the concrete either before or during its mixing. You know, either when it's being mixed at the ready mix, or while they're mixing it on the side, to alter its properties. See that? We want to change the properties of it, such as workability. See, make it more workable. It's easier on the workers. If it's too stiff, if I cannot add too much water to it, the mix is going to be too stiff. It's not going to be easy on the workers. Okay? So to improve workability, that's something you do. Curing temperature range. We want to cure. Curing meaning we want the concrete to dry and set to become really dry and then workable later on. And then set time or color. Sometimes we want it to set, and it means dry and be workable. We were able to step on it in a timely manner. Or color. Color is considered as also an admixture, because sometimes we would like to put sidewalks or crosswalks in the middle of the street and color them red. So that is an admixture. Okay? All right. Again, please interrupt me any questions you have. Okay, concrete has high compressive strength and low tensile strength. I'm gonna repeat this sentence probably 100,000 times this class. Okay, very important. This is what concrete is all about. It's very strong in compression, but very weak in tension. So if let's take a 1-inch diameter rod made out of concrete. If you try to compress that, you're gonna find it very strong. But try to attach it to a machine and try to pull on it in tension. It's gonna break right away. Okay? So, and then we'll explain how the compression is easy to understand, because you have a column, concrete column, you compress it, that's a compression member. But how do we get tension in concrete? We'll explain that later, okay? Because we don't get a concrete column and then tension like that. That's not practical, all right? So, but I want you to remember this. The concrete as a material is very strong when you compress it, but very weak when you tension that. And we'll explain how you tension that. Reinforced concrete is a combination of concrete and steel. See, I mentioned that at the beginning. That's why we call it reinforced concrete. The minute we add steel to it, it becomes reinforced. So it's a combination of concrete and steel. Okay? The reinforcing steel is used to resist tension. Now, if we're saying that concrete is strong in compression, weak in tension, what happens if this concrete is subjected to tension? We have to give it help to resist additional tension that the concrete cannot resist. Guess who's going to do that? The reinforcing bars. The reinforcing. That means the steel is strong in tension. I am sure you did the in materials lab. You took a piece of steel 12 inches long, you attach it to the machine, and you apply tension force on it. And what happened in the middle of that? It starts to neck down. We call it necking. And then ultimately the bar broke. But it took a lot of force to do that because steel is strong in tension. Now, I just said concrete is strong in compression, weak in tension. Does that mean steel is strong in tension and weak in compression? No. I used to tell the student to wait a little bit. No, I'm going to answer it now. I used to wait till we get to the column chapter to answer that, but let me answer it now, and then we will talk more about it when we get there. The answer is no. The steel is strong in tension, and it's strong in compression. Okay, and we will illustrate that when we get to the column chapter. So the steel is a good material. You can depend on it in tension and in compression. All right. So the reinforcing steel is used to resist tension. Reinforcing steel can also be used to resist compression columns. See, I just said that. So we can also use compression. That's why we put rebars in our columns. We never build columns without steel. Okay, we'll talk much more about this stuff. You're gonna hear a lot of stuff about that. All right. So advantages of reinforced concrete. See, everything we do there's an advantage and disadvantage. By the way, there's two organizations. One is ACI. That's the American Concrete Institute. They always try to advertise and encourage the usement of reinforced concrete to build buildings. But we also have the AISC, the American Institute of Steel Construction. They try to encourage use steel for buildings. So of course everyone has advantages and disadvantages. All right. So you'll cover the same when you take steel design 455. Of course, those organizations look at it from the commercial standpoint. Everybody wants to sell their products. But we as engineers, we have to be aware of what are the advantages of each one, and then use that. And let me tell you, the economy is a big factor of it. The economy is a big factor. One time I worked on two huge water tanks. Okay, each one contains 16 million gallons. So at the beginning of the project, the first thing we did is we did an analysis. Do we build it with concrete tank, or do we build a steel tank? So we did the engineering economics analysis. I'm sure you had that class. And then at that time, because it's a time factor, depends where you are in the marketplace. What's the price of concrete? What's the price of steel? So we found out that if we build it with steel, we would save $2 million. And then that's how we built that. And that's unfortunate for me because I like concrete. I'm a concrete guy. So we went ahead and built it with steel. Because at that time, China was booming and they were buying all the cements out of this country, believe it or not. So the concrete was expensive, steel was cheap. So that's why it was economical to do it with that. So one of the considerations you will consider is the economy of the material. Do I build a building with concrete or do I build it with structural steel? All right. So what are the advantages of reinforced concrete? High compressive strength related to unit cost. Concrete per se is cheap material. The cubic yard of concrete costs about $80 to $90, I believe, somewhere around that. And just to give you a perspective of that, a concrete truck carries about 9 cubic yards. And every cubic yard is about 80 to, call it $100. So a truck of concrete costs $900, roughly. So it's not expensive. All right. So high compressive strength relative to unit cost. Okay. High resistance to effects of the fire and water. Right. I mean, the more water you put on the concrete, the stronger it gets. But the more water you put on wood, you ruin that. And the more water you put on steel, if it's not protected with paint and all that, you ruin that. But the concrete loves water. Second, fire. It's not easy to burn a concrete building, but it's very easy to burn a wood building. And then also steel, under very high temperatures, they will yield, they will melt per se. Okay, so high temperature resistance is great for concrete. Reinforced concrete structures have high stiffness, very stiff buildings. Wood structures are very flexible. Visualize a 4 or 5 story wood building and try to, shake it up with a machine or something. It's flexible. It's gonna shake. It's gonna flex back and forth. But try to do the same with a concrete building. It's not gonna move. Okay, so it is have high stiffness. Where does that make a difference? In seismic, in earthquakes. Okay, but sometimes having too stiff of a building could backfire at you. Okay, could backfire, but you need this stiffness if you are building very high-rise buildings. That's why you see wood, you can go 4, 5, probably 6 stories. You will not see a 10-story wood building. Okay, yeah, they're nice and they're flexible, but the strength of them are not that great. But concrete, the highest building in the world now in Dubai is built out of concrete. Okay, so this is what the stiffness is advantage for concrete. Low maintenance cost. You put it in, you forget about it. Concrete doesn't need any maintenance except if it starts to crack and all that, and we will talk about that. So very low maintenance structure. Where wood, you have to paint it, you have to, even steel, you have to paint every so often and all that. Okay, more advantages. Reinforced concrete structures have a long service life. If a building is done right, it can serve you 100 years with no problem. No problem at all. 50 is definitely a given, no problem. Okay, so very, very long service. Reinforced concrete is often the only economical material for footings. Okay, I wouldn't say often. It's always. I would replace this with always, because we don't build footings with anything else but concrete. I know years ago they used to build footings using wood, but what happens to wood after 10, 20 years? They're gonna rot. Okay, but the concrete, nothing happens to it. Okay, so this word should be always. Reinforced concrete, always the only economical material for footings, floor slabs, basement walls, and piers. Okay, so again, anything below ground, concrete. Reinforced concrete offers architectural flexibility, meaning that the architects love that because the concrete can follow the form of the formwork. You can make it circular, rectangular, square, whatever you want to do. But wood, you can't do that. Steel, you can't do that. Okay? Now, lately, they are able to bend steel, make like a curved beam and all that. But mostly are straight members. So, but the concrete, whatever form you put in, you put this material in, and then it'll take the shape of the form. Okay, reinforced concrete has local materials for aggregate and only small amount of cement and steel, which are items that may not be available locally. That's why third world countries, 100%, I would say, maybe 99.9% of the buildings they build is concrete. Why? Because they have abundant material. They have sand, most countries, and they have aggregates. Yeah, they maybe they don't have cement and steel, but those are small materials compared to others. They'll just bring them from outside. They'll just import them. Okay, but the majority of the materials are available, usually local material. Let me get off on a little tangent here, and I will do that from time to time to illustrate something, otherwise I will forget about it. I went to a conference last year, and this topic was discussed. Believe it or not, the geologists are telling us now as engineers that the state of California does not have enough construction material to last us to so many hundred years. You won't believe that. Like, yeah, we have a lot of deserts, we have a lot of mountains, but they say no. We do not have enough materials to last us, for hundreds of years. California doesn't. Okay, so they have to import from other states in the form of sand or aggregates and all that stuff. So if you hear that term, don't be surprised, but that is a fact. The geologists look at that, and they look, of course, at the sand and how suitable it is for construction and the materials and all that stuff. Okay, labor skills are not as high for reinforced concrete construction when compared to some other common materials such as structural steel. Labor skills are not, everybody can form a box and then put the box vertical and fill it with concrete. But not everybody can go and build a 2-3 story building and made out of structural steel. It needs more experience, more professional trained people, more equipment. Okay, so that's why, again, in third world countries, you will see more concrete because the labor skill are not as high as other material. Of course, structural steel, yeah, you need to have cranes, for example, right? Cranes. Without cranes, you cannot build those buildings. You need people to operate the cranes. People knows how to put the beams and columns together, okay? Just like Legos and all that. So that's what that means, labor skill. Those are the advantages of concrete. Of course, there are disadvantages. So what are the disadvantages of reinforced concrete? Concrete has a low tensile strength. See that? We already mentioned that. Concrete has a low tensile strength. So I cannot build everything by concrete. I need to bring other material. Why? Because it's low tensile strength requiring use of reinforcing steel. See that? So that's a disadvantage. It would be beautiful if the concrete as a material was strong both in tension and compression, but it's not. Excuse me. Okay, forms are required to hold the concrete until it hardens. That's another disadvantage. See, if you want to pour a column, you have to put a wood form and support that, then pour the material inside. But if you want to put a steel column, the column is ready. All you have to do is stand it up and put your bolts in. That's right. That's an advantage to the steel and disadvantage. I'm sorry. When I say steel, there's two types of steel, so we don't get confused. The steel we're using here is reinforcing steel. The other steel that we build buildings with, we call it structural steel. So I'm going to differentiate when I speak. So if I'm doing a structural steel building, I bring a column, you can just stand it up vertical and then put the bolts down. But then if you are doing a concrete column, you have to form it, put the reinforcing steel inside, then pour that. Okay? So that's an advantage to the structural steel, disadvantage to the concrete. Forms are required to hold the concrete until it hardens. Once the concrete hardens, you strip the form, right? We'll talk about that. In addition, false work may be necessary. False work, just the false. These are the stuff that we support with. When you drive on the freeway and you notice a bridge being built, you will see the forms that they shape the bridge with to pour the concrete in. But underneath that, you will see so much wood going right, left, up and down, and all that stuff. That's the false work. The false work is mainly there to support the forms so that it doesn't fall down. Okay? So it says false work may be needed form and false work are expensive. Okay, very expensive. Sometimes, believe it or not, the cost of that it goes up to about 60%, 50 to 60% sometimes the cost of the form work. That's why a lot of companies out there were generated, created, and then they came up with different designs of form work. Because you know the typical contractors, again, they use the wood and then they throw it away. You know, but now the companies are trying to make wood and forms so you can reuse. We have something called slip form. That means you, like, let's say you're building a wall. You have a form that you put the wall in, and then when you're done, you slip it up another floor. You pour it, you slip it up another floor and pour it. So all kind of form work out there, but it is very expensive. Concrete has relatively low strength when compared to its unit weight. Okay, I want to talk about that a little. So the concrete has relatively low strength compared to its unit weight. So what does that mean? Before I say that, first of all, the density of concrete is 150 pounds per cubic feet. To make it register in your head, if you buy a basketball at Walmart, the basketball will come in a cubical box of cardboard, and then the ball is sticking out from all four sides, right? If you take that box, which is roughly a cube, the side of this cube is 1 foot high, 1 foot wide, and 1 foot deep. That's a cube. That's a cube feet. You know, if you take 1 foot times 1 foot times 1 foot is 1 cubic feet volume. If you take that box and fill it with concrete and weigh it, it's gonna weigh 150 pounds. See that? This is how you figure how heavy the concrete and what is the density. So can you imagine 150 pounds? That's the weight of a person. And it's only 1 by 1 by 1, the basketball box. So it's heavy concrete. So in order to if you put a beam that is 30 feet long, and say typical beams are going to be about 16 inches wide, maybe 24 inches deep. Can you imagine how heavy that is? Very heavy. Very heavy. Okay? So that's what it says. Concrete has relatively low strength when it compared to its unit weight. So the things you're going to design are going to be very heavy. All right? That's why when we start design, you will see us doing, we're going to have a dead load and a live load, but we're going to also have the own weight of the beam, the own weight. Because before the beam can carry anything else, it has to carry itself. So we add the own weight of the beam into the calculation. All right, and we'll see how we do that. Any question on that? So that's what this is very important statement, is that yes, it's a good material, a strong material, but when you build a beam with it or a column, that beam itself is very heavy. It has to carry itself in addition to the applied loads.
I have a question.
Yes.
Is the weight of the beam considered dead load?
Yes, very good question. The weight of the beam is considered dead load, but that's not the only dead load you will have in the structure. So we will add it to the dead load. So what other dead loads the building could have? Think about this. You have a room in a hotel. That room is supported by beams below that. Okay, so the weight of those beams are dead load. But what other dead loads we have? The weight of the slab that you're standing on is a dead load. We're also going to have the dead load of that. The weight of the tiles you put on the slab is a dead load. The weight of if you run underneath electrical conduits, fire sprinkler conduits.
Like water piping and air ducts?
I'm sorry?
Like water piping and air ducts as well?
Yes, those are all considered dead load. And you will see when we do the project, that will be taken into account. So these are all dead loads, and the weight of the beam is the dead load. Thanks for that question. And we'll talk much more about that. We'll see how we do that. Of course, while we're here, let me just say one more thing. So in addition to the dead load, we have a live load. So what is the live load? The live load is the weight of the people who are going to use that, and the weight of the furnitures you're gonna buy, living room set, the bedroom set, whatever you wanna buy. These are live weight. Okay, live loads. All right. We'll talk much more about that. Any other questions? All right. Another disadvantage is the high unit weight translates into large dead load and corresponding increase in bending moment. See, we already covered that. So of course, if my beam is gonna have a high dead load, that's gonna lead to a larger moment. Why? Because for simply supported beam, the moment is WL square over 8. So the higher the W, the higher the moment. So that's what it means. The high unit weight translates, that means leads, into large dead load, and as a result corresponding to a larger bending moment. Okay, it's very obvious. Concrete beams are relatively large. See, I just mentioned that. Usually 16 by 24, roughly. Those beams in parking structures you see, they are roughly 18 inches wide, 20 by about 30 inches. Huge. And the spans on those are 60 feet. 60 feet long, 60 to exactly comes out to 63 feet, 64 feet. All right? So those are very heavy. So that's why concrete beams are relatively large, which leads to, for example, larger story height and taller buildings. So what this means is that if my beam is, let's exaggerate a little bit. If my beam is 30 inches high, what happens when you have a 100-story building? Okay, it's going to make a difference because the height of the building is going to be the height of that beam, the depth, plus, of course, the depth of, because let's say you want a floor that is 9 feet clear. Most commercial buildings are 9 feet clear. Above that suspended ceiling, you have at least 3 feet. Why? Because you have to put a structural member there, let's say it's 24 inches, and then those piping has to go across. So the more that space, the higher that space is in a 100-story building is going to make a difference. And why do we care? We care because that means when you put the plaster on the outside, then you're going to have more material on the outside, right? Then what happened when we analyze the wind load? The higher the building, the higher the wind load. What happened to seismic load? The higher the building, the higher the seismic load. So we try to minimize the depth, the height of the building. But in reinforced concrete, because the beams are deep, then you're going to end up with that. In steel, for example, structural steel buildings are known to be lighter structures than concrete, absolutely lighter. The weight of the steel structure is much lighter than the concrete structure. Why? Because they can be, if you go 36 inches concrete deep beam in structural steel, you probably can get away with a 24. All right? So, because the densities are different, and we'll talk about that. All right. So larger story heights and taller buildings. Okay. Concrete properties can vary widely depending on proportioning, mixing, and curing. See that? We go again back to proportioning. Proportioning means how much sand do I put? How much cement do I put? How much water do I put? How much aggregate do I put? You can do a mix design that gives you a concrete strength of 2,000 pounds per square inch. And we use that for what? For sidewalks. We use them for walkways. We use them for patios. But if you are doing a structural building, you need 4,000 PSI at least. You can get away maybe with 3,500, but minimum 3,000. But most buildings out there are built out of 4,000. See that? So that's why you proportion anything you want. Then how you mix that? Okay, you have to mix it well in order to get everything to, because in the process of concrete, there's a heat of hydration process where the water chemically, there's a chemical equation really that takes place between the cement and the water and then the other materials. Remember how in chemistry you took A plus B gives you C plus heat, right? Heat could be a byproduct of a chemical equation. One of the byproduct is heat. And then the reason I say that is that if you pour concrete today and you go the next morning and you put your hand on it, you're going to feel it very warm. That means the heat is a byproduct of that chemical equation. Okay, so there is definitely chemical activities going inside. So the better you mix it, the better the chemical reactions and equation is going to take place. And then curing. What is curing? Curing is a lot of people you see probably they pour concrete today and then in the morning you see they putting water on it. They get some cold water, room temperature cold, and they put it on the concrete. When you put it on that, you start seeing it fizzles. You start seeing bubbles coming out of that, right? Again, concrete loves water. So this is curing because the idea is to keep it wet at least for 7 days. Okay, the more you keep it wet, the better it is. Because the more you keep it wet, the better this chemical operation that's going place, the heat of the hydration process is better. Okay, because the reason is this. Right? Go ahead.
If you don't water it, ends up cracking, right? Or
yes, absolutely. If you don't water, it cracks. Why? Because let me cover the first one first. Remember, we put water in the mix. That water is needed for the chemical reaction between all the materials. If the sun comes up on this concrete we just poured, what's going to happen? Evaporation is going to come up as a result of heat. So that means we're going to lose water from the mix. Well, that water we counted on to be for the chemical reaction, right? So our chemical reaction is not going to be as we designed. That's why we put water on top so that if anything is going to evaporate is the water we just put in and the internal water remains. Okay, that's one thing. Second, like he mentioned, is that cracking. Okay, again, if the water is evaporating and all that stuff, then that means the volume of the concrete is being lost to evaporation. And what happens when the volume is decreased? The material is going to move. It's going to shrink. Okay, it's going to shrink as a result of that loss. And when something shrinks, it's going to crack. Very good comment. Thank you. All right, so that's another one. So curing, very important. Sometimes on the freeways, instead of dumping water on it all the time, they go ahead and cover it with very thick fabrics, and they keep that fabric wet because the fabric would keep the moisture down versus that if you just spray it on the top. Okay, so there's a lot of ways to do it. And also you can curing by spraying some chemicals on it. We call it chemical compounds, chemical curing compounds. When you do that, you will see that the concrete gets a color, but then ultimately that color goes away. So there's many ways, but the quickest way, fastest way, and the easiest way is to just dump some water on it. Again, curing is a very important term. Mixing is when you mix it and then the proportioning of it. Again, guys, I'm sorry, there's no numbers as you can see, but we need to understand the material before we start designing that, right? You will see when we start designing, we're going to come back to all. I'm going to remind you, remember when we said that, but we need to understand it as a material. Okay. Second is codes. In this country and all countries, but this country is the best, is definitely the first, number one. We have the best codes in the world here. Everything we do, you have to follow a code. For example, in the building and the concrete, ACI, I would say the best code in the world. American Concrete Institute. 318-14. 318, when you say this number, is related to building construction. There's other numbers that could be here, could be a different number. That would be for tank construction. But everything we're going to deal with is 318. 14 is the year. This is 2014. Now we are up to 2019 on the syllabus. If you look at it, I listed 2019, but you don't need to worry about that. The code changes every roughly 5 years, but not much. It doesn't change much, okay? But they always change. So this is 2014. All right. So this is the code we're gonna comply with. You don't have to buy it. You know, if you have time, you go to the library, get a copy of it, look at it online. Sometimes you will see PDFs online for older versions. Definitely, you know, look for that and you will see. Very important code. Okay, we have to follow that. Now, this code, who comes up with this code? Professionals, professors, practicing engineers who've been working a lot with that, people who are doing research on this, and then they keep improving the material. Every time they come up with a new thing, they change the code but the gist of it is still the same. It stays the same. So again, ACI code is the #1 in the world, and a lot of countries adopt that. But what they do is they change it a little bit and they call it their own. But the meat of it, the source is ACI, for sure. But because every country is different, like weather-wise and earthquake-wise and all that, so they go ahead and adjust it to their needs. But this is the building codes. Of course, in structural steel, there's AISC code also. And then in wood, there's another NDS code and all that. All right. Now, we're going to take the ingredients and start talking about that. The cement, we call it Portland cement. Okay, we call it Portland cement. It doesn't mean that it's made in Portland. No, this is the name of it, Portland cement. There's different types of cements out there. Look at that, type 1, type 2, type 3, type 4, type 5. Who's gonna select which type to use? Is the person who's doing the mix design. The person who's doing the mix design, when he knows or she knows what you're looking for, they're gonna decide what type of cement to use. All right, so let's see the difference here. Type 1 is common, all-purpose cement. You want to do a sidewalk, you want to do a curb, you want to do a walkway, you're going to do a patio, type 1 works for you. Okay? Now, type 2, low heat of hydration and some resistance to sulfate. Low heat of hydration, that means the heat byproduct is not that much. Why do we care about that? When you build a massive structure or like a very thick structure with all that heat inside, can you imagine how hot that thing is going to get? It's going to lead to cracks. So if you are pouring a very thick structure, you want to specify type 2 because you want low heat of hydration. When they build dams, guys, out there, you know how thick the dams are. Sometimes they run water piping inside, just like a radiator for the car. They run water piping inside, and inside those lines, they run cold water for so long until the concrete cures, until this heat of hydration dissipates. Then they turn the water off. But it's a problem when you're doing something very thick. Inside of that, there will be high heat of hydration, so you will pick up this kind. And then also resistance to sulfate. What's sulfate? You know, you took chemistry. Sulfate is a material that could lead to, if it's contact with concrete and this rebar, especially the steel, it would rust it. Okay, and then it will bother the concrete and then hurt the concrete. Sulfate usually exists in soil. You know, we sometimes we call it a hot soil. That means it's high in sulfate. Okay, so if you are doing something at grade where it's going to be in touch with sulfate, then you will do 2, like footing, foundation. The foundation is going to sit on the ground. So then that's high in sulfate. And then you will know your soil because you're going to have a soils report from the geotechnical engineer, and he'll tell you, he or she will tell you high in sulfate, low in sulfate, and the mixed engineer, he will have that information. Type 3, high early strength, high heat of hydration. See that? This is high heat of hydration. You don't want to use this in dams. You want to use this in dams. But look at this. Yes, it's high heat of hydration, but high early strength. That means if you pour a manhole in the middle of the street and you want to open the street, this is the one you're going to use, because you want the concrete to cure quick and then open the street up. Number 4, low heat of hydration. Again, this is another one you can use for dams. Number 5, use for concrete with exposure to high concentration of sulfates. See that? So sulfate wise, you can do 5 or you can do 2. So again, the mix engineer is gonna decide those stuff. Again, Portland cement. Concrete made with type 1 Portland cement must cure about 2 weeks to achieve stuff. I'm sorry?
Can you go back to the previous page, like, for a second?
Yeah. This one? You got it?
I got it. Yeah, you can move.
Okay, thank you. So Portland cement now, concrete made with type 1 Portland cement. Everything we're going to read here, I probably mentioned it, okay? But we'll see what we highlight. Type 1 Portland cement must cure about 2 weeks to achieve sufficient strength to permit removal of forms and application of smaller. So when you form the concrete column or beam, you have to wait about 2 weeks. That means 14 days, okay, before you start stripping the form, okay? When you strip the form in 2 weeks, yes, the concrete is going to be fine. But the concrete is not ready to apply the load to it, okay? It's not ready. It's ready to stand on its own, but it's not ready to carry the applied load. When is it going to be ready to carry the applied load? In 28 days. This is a magic number for concrete. In 28 days, not 27, not 29, 29 is fine. Not 27, not 26, 28 days. Okay? Why is that? Because they did a lot of research and then this is the amount of strength that the concrete will achieve at 28 days. So we design for that number. We'll talk more about that in a little bit. So concrete made type 1 Portland cement reaches design strength in about 28 days. Now, again, I get off on a little tangent. When let's say we are doing a beam and then we're gonna pour it with type 1. So yeah, we're gonna strip the forms in 14 days, but I cannot lay anything on that beam until it's 28 days. But at the same time I pour that beam, I'm gonna pour 2 cylinders with it at least, or more than 2. 3 at best is 3. Okay, in the lab we do 2, but in real life do 3 cylinders. Those are the 6x12. You saw those in the lab. So what happened is usually at 7 days they will break one of the cylinders to see how strong it is. In 14 days they'll break one. And if that's what they were shooting for, then you tell the contractor, go ahead, strip the form. And then in 28 days you break one. That 28 days is the F'(C) of concrete. That is the compressive strength of concrete. Every problem you're gonna see here is gonna have the F'(C) in it. That is the compressive strength of the concrete at 28 days. All right? I'll remind you of that. Concrete made with type 3 Portland cement reaches design strength in 3 to 7 days. See that? If you want something to get stronger before that, before the 28 days, look at this. It reaches design strength in 3 to 7 days. All right? Very, very, very impressive. Let me get off on a little tangent again. We did a parking structure. I did many parking structures before. So the contractor pours the beams on Thursday. This is typical standards out there. On Thursday, they pour the beams. Look, now remember, the beam is 63 feet long, about 20 inches wide by 30 inches deep. Just visualize how big that beam is. Of course, beam like that, we cannot design with conventional concrete like we're doing here. We have to use post-tension, and I'll talk about that a little bit later. So, but just to convey my idea or my discussion. In those post-tension beams, we put something called, like, it looks like a rope, but it's a steel rope, strands we call them. Okay, and we wait now from Thursday till Monday. On Monday, the contractor will come, and then of course you lay these ropes in it, metal ropes. They are anchored at one end and then loose at the other end. So after on Monday they come and then stretch those. They catch them from the free end and they apply a tension pressure on it. So they stretching them until certain PSI as designed, and then they lock it. Okay, so once they lock it, this strand is gonna try to go back because it gets stretched. It wants to go back to the original length. It ends up putting the entire beam in compression. Okay, that's very, very brief introduction to the post-tension, but I'll talk much more about that. The reason I'm mentioning that is this. After they do that, remember, it's Thursday to Monday. Guess what they do? They strip the forms. It's unbelievable. It's unbelievable. You say, you put on Thursday and you're going to strip on Monday? Is the concrete hard enough to do that? Is the concrete hard enough to take all that compression that you applied in those cables? Is it hard enough to carry its own weight, as heavy as it is? Believe it or not, it is. Why? Because they use high strength concrete. Okay, so very important. We'll talk much more about that. Okay, concrete made with type 3 Portland cement produces high heat of hydration, more likely to cause cracking. See that? If it's too thick, you're gonna get some cracks if you're not careful. Concrete used in seawater or some soils may be subjected to attack by chlorides or sulfate. So if we're near the ocean, near the beach, you need to be careful. You see buildings in the Gulf states like Saudi Arabia and the Emirates and all that. If you drive along and you see those buildings along the coast, you will see how the sulfate and the chloride just attacks the concrete. You see it. It's very obvious. Very obvious. So you have to be careful if you're building near the seawater. Okay? Because even if it's not in touch with the water, but the evaporation of that is going to carry the salt with it and then attack the building. All right. Now we just talked about the cement. Next, we're going to go to the air and the admixtures. Remember we said those are two ingredients? So what's an air entraining admixtures? Air entraining admixtures for concrete must conform to either ASTM and STM. We don't need to remember those. But ASTM, you know that from your materials lab and all that. It's an American standard, okay, for materials. So everything has a number. But again, it's not important here. And the reason they have this is that if you want to test that material, you have to follow their guidelines. Okay? So we have to conform to these stuff. Air entraining admixtures produce small air bubbles in the concrete. So what happened is, okay, the mixed plant is, the concrete is getting mixed, right? So they go ahead and inject bubbles. You've seen bubbles, right? And parties and birthday parties and all that stuff. So they inject bubbles into the mix, believe it or not. And those bubbles stays, not on the outside, inside. They, if you stick something and blow bubbles into it, those bubbles, and you mix it, the bubbles gonna be there. Now, why do we do that? Why do we do that? Because back east, when we have a freezing and thawing cycle, we don't have it here in California. But back east, in the winter, the concrete freezes and then it thaws and all that stuff. What happens when water freezes? You put a can of Coke in your freezer and leave it till tomorrow, you'll come and weather, it explodes, right? Why? Because the liquid expands when it freezes. So if the concrete roadway or bridge is wet, okay, and then it starts, of course, those molecules of water is gonna go through the porous point of the concrete. So they're gonna go inside, and what happened? They're gonna freeze. When they freeze, they're gonna expand, and when they're gonna expand, they're gonna crack the concrete. So when you provide those air bubbles and this happens, the expansion is going to go into those bubbles because they're going to be voids. The bubble is not going to stay a bubble for a long time. The bubble is going to pop, but this is going to create a void. So when the expansions happen, it's going to go into that. All right, that's why. So air in training admixture produce small air bubbles in the concrete. When water in concrete begins to freeze, it expands. See that? The expanding water moves into the space in the air bubbles. So we're just creating a space for that to move into. In the air bubbles, the water has room to expand without creating internal pressures in the concrete. Because if you create internal pressure, that's what's going to lead to cracking. But if you create that void, then it's going to be fine. Concrete without entrained air will deteriorate due to freeze and thaw cycles. Expansion, contraction, expansion, contraction. Important for bridge decks and other concrete members exposed to freeze thaw cycles. We talked about that, right? So this is, when you do bridge decks, then they always recommend air in training concrete. And it's easy, you just blow bubbles in. What other admixtures that are out there? Again, believe me, the class is going to get much more exciting than this, guys. But we have to cover that. Okay, we have to cover the material. But after, once we start punching numbers, equations, derived formulas, you're gonna be excited. I hope. Okay, other admixtures. Accelerating admixtures, such as calcium chloride, reduce curing time. Let's say you want to cure the concrete early so you can open the street. You add calcium chloride. That is called accelerating admixture. That means it accelerates the curing. All right? Again, who's going to decide that? The mix engineer, the design engineer. You tell him or her, I want to open my street in 3 days. They're going to design a mix and they're going to add calcium chloride to that. All right? Calcium chloride can cause corrosion in reinforcing steel, aluminum, and other materials. So you have to be careful. Yes, it's good to do this, but it's going to also corrode the materials. Now, if you have to do it and you don't want the corrosion, then sometimes rebars are painted, right? They paint the rebars before they put them in there. Retarding. Now, accelerating is increasing. Retarding is slowing down. Okay? Slowing down. Retarding admixtures slow the rate of set of concrete and reduce temperature increase. Sometimes we don't want the concrete to cure quickly. We want it to take its time. What's a good example of that? And I've seen it so many times on the jobs. You pour let's say you pour a driveway for a house. And then you will see that when they form the driveway, you're probably going to see 2-3 guys. They're going to take a day or two to form it, and that's it. They're ready. They call for the concrete. When the concrete trucks gets there, you will see about 20 guys out there. Remember, 3 guys form it, 20 guys there to put it down. Of course, this is for a nice sized driveway. Why is that? Because once you put the concrete down, if you don't have enough people to work it out and flatten it and then make it as smooth as you want to, the concrete is going to set. If the concrete sets too quick, it's going to harden. And once the concrete hardens, guess what? Those guys cannot smooth it anymore. That's it. That's it. They lose it. And then if they lose it, they have to come back, break it, and redo it. So in cases like that, you have a large piece of concrete to finish. We call it to finish. You need to have retarding admixtures. So you tell the mix engineer, or he or she will know what size you're trying to do, and they will add those chemicals in it. So it will, and you don't care if it's a driveway. It takes 2-3 days, 4 days to cure. Who cares? But you need enough time to finish that. Slabs in a parking garages. Okay, those guys are on their knees all the time, finishing that. All right, and then putting certain textures by hand. You have to give them time. All right, that's a good example of that. Retarding admixtures are useful when a large amount of concrete is to be placed and it is important to reduce temperature. See that I just mentioned that. This is it's a large piece, is important. He doesn't say why, but it is because once it's set, then the guys cannot do the finish. Okay, and it reduced to reduce temperature. Also, the larger the piece, the larger temperature. You don't want it to get too hot. Okay, other admixtures, retarding admixtures prolong the plasticity of the concrete. Okay, this is also part of what I mentioned. Plasticity meaning that the concrete is still soft, workable, plastic, like a melted plastic. That's what plasticity is. Of the concrete, increasing the bond between successive pours. Okay, so the plasticity is it remains so you can finish it. Also, the plasticity is important. Why? Because if you have a huge piece of concrete, you cannot put it all in one day. You have to come the next morning and continue that. Of course, when we do that, we call that a construction joint. They put a form at the joint, and then they come back in the morning, remove that form, spray it with water again, and then pour against that. Now, if the concrete is still have a nice plasticity, when the new concrete bonds to the old concrete, is going to bond well. If the old concrete is already dry and the new concrete is wet, it's not going to bond well. All right, that's what it means here. Again, the mix designer is going to do all that. Super plasticizers are made from organic sulfates. This is just a specific admixture. You know, they are made from organic sulfates. And then the super plasticizers maintain workability with reduced water-cement ratio, usually using glass cement. So this is very important, the water-cement ratio, W/C. You've seen it in your materials lab, right? So water-cement ratio, that means the amount of water over cement. It could be by weight, like 10 pounds of water over 50 pounds of cement, or 10 cubic feet, say cubic feet of water divided by 20 cubic feet of cement. As long as you're consistent, it's okay. It's going to be defined. So the water-cement ratio is that the higher the water, the higher the ratio, right? Because the numerator is the water. The lower the water, the lower the ratio. A standard or typical value of this is 0.4, 0.45. Okay, so in order to maintain a low water-cement ratio, the concrete is going to be very stiff for the guys to trowel it in. So if you use this admixture, super plasticizers, they will definitely not increase the water-cement ratio, it's going to increase the workability of it by maintaining the water-cement ratio. All right, so that's a big advantage. And then also, they are used to produce self-consolidating concrete. Self-consolidating concrete is that sometimes you're doing like, let's say a shower or something. The contractor will go ahead and put concrete in and leave it. It will settle itself. You know, it's self-consolidated concrete. It has plasticity in it. It will level itself off. You don't even need to put trowels in it. Okay, with the self-consolidated concrete SCC, vibration is not required to get concrete to flow around reinforcing rebar and in congested air. So it will go itself. But honestly, you don't see that a lot on construction site. You see it sometimes like in bathrooms and things like that. Because if we're gonna do around rebars, we wanna make sure that this is vibrated and then it goes around this. I'm not going to depend on the self-consolidated concrete to do that. Okay, so those are the admixtures. See that? We covered a lot of admixtures. But again, in summary, those are the chemical compounds you add to the mix to achieve one of those goals. All right? So that's what that is. Again, who decides if you work with the ready mix plant as an engineer, you're going to deal with that. All right, and if you give them a mix you use, I need to do a patio. They will know what to give you. They will know all that stuff. I am building a bridge deck in Anaheim. They will know the weather. They will know whatever they will give you. But you have to tell them what's the F prime C. I need 4,000 concrete to build a bridge deck. I need 4,000 concrete to build a water tank. The guy will know what to pick here. And here in this course, we're not gonna design this. We're not gonna worry about that. But unless if I ask fill in the blanks question, I might ask you something from here. But we're not gonna use that in design. All right. So that's it for concrete. So we've covered the concrete as a material. Next is properties of concrete. Sorry, no, we're still there. I'm sorry, I thought we were at the steel. No. So we're still with the concrete, but at least we covered the mix of the concrete. So what are the properties of reinforced concrete? Compressive strength. See that? Again, the compressive strength. Concrete is strong in compression, weak in tension. The compressive strength, we refer to it as right here. This is the first time you saw it, F prime C. This is going to be in every problem in this class from now on. It's going to be on every plan you see out there. This is the compressive strength of concrete. When we say I need 4,000 PSI concrete, that means F prime C is 4,000. That means at 28 days from pouring this concrete, the compressive strength of it is going to be 4,000 PSI. All right? The specified compressive strength of concrete is denoted by the symbol F prime C. Compressive strength is determined by testing 6 by 12 inch cylinder at an age of 28 days. See that? In Europe, they do not use cylinders. They use cubes. They pour, some countries, they pour cubes and they break the cube. But in this country, the cylinder is what is used. For most applications, the range of concrete is 3,000 to 4,000. I said that. Okay? But for buildings, definitely the 4,000. For foundations, 3,000, 3,500. In the project, I gave you that. I said 4,000 above ground, 3,000 below ground. Okay? And why? Because we don't need and you will see, for the foundation system, we don't need as high concrete. So we can save some money by doing that. Okay. For pre-stressed concrete, that's the one I just mentioned. The range of the concrete strength is 5,000 to 6,000. See that? This is why they could strip the forms on Monday if they pour Thursday. All right? So this is what you do pre-stress, you have to do high-strength concrete. All right? Now, for columns with high axial loads, lower stories of tall buildings, concrete with strength in the range of 9,000 to 10,000 PSI. Look at that. Remember, the typical is 4,000. Can you imagine 10,000? When would we do that? In the highest building in the world, in Dubai, what do you think the first floor columns, what size are those? You can just imagine how big they're gonna be, right? So of course they're gonna use this kind of PSI. Because remember, from strength of material, pressure equal force over area, right? Pressure equal force over area. So force over area. So the area is equal to force over pressure, right? So the higher the pressure, the smaller the area is gonna be. That's why. This is the idea. Again, pressure equal force over area, and then the force, the area is equal force over pressure, and the pressure is the 10,000 psi. You know, this is the pressure. Any questions? So that's why we do have, but it's not easy to work with high strength concrete. It's very critical, very dangerous. You have to be very careful with that. But when you're doing 100-story building and all that, you're gonna go that way. And of course, it's gonna be much more expensive. Why? How do you think you get from from 4,000 to 10,000. They're going to add a lot of chemicals to this. They're going to add a lot of admixtures to that to get to this level. Okay, and then those are expensive. All right. So we're talking about F prime C. How do we determine that? We said we do cylinder, and then we compress it. You've seen that. And when it breaks, you will get this F prime C. Now, this machine is not going to give you a stress, most likely. It's going to give you a force. It's going to give you a force. So many pounds, so many kips. If you the top of the cylinder, the diameter is 6 inches. So what's the area? Is pi r square. The r is 3 inches square, 9 times pi. That is the area. So you take that force from the machine divided by the area is going to give you the stress. Force, stress equal force over area. Or if you haven't adjusted to stress, in high school we used to refer to it as pressure. Remember, in high school, pressure equal physics. Pressure equal force over area. In college, we call it stress in concrete. Stress equal force over area. So the force is coming from the machine. The area of the cylinder, that's the F prime C. So at what force this is going to break, you take that force divided by the area, that's your F prime C. And if you are calling for 4,000 PSI, you better get 4,000 and more. But most of the time, the designers will, if you ask for 4,000, they're going to give you 4,200, 4,300, because nobody wants to take a chance. You put a big bridge deck, and then they're going to test it in 28 days. If that F prime C is not what they called for the bridge, guess who's responsible for that? Is the material supplier. Who wants to take the responsibility? See that? Guys, let me tell you this, and I keep repeating that. Our job, our major, our daily duties comes with very high risk, comes with a lot of liability. This is one example. You're a mixed design engineer, and then they ask you for 4,000 PSI for a bridge deck. And you made a mistake, and then after 28 days, they tested the cylinder and it came out 3,000. You think they're going to accept that bridge? No way. No way, because everything was designed based on that value. There's millions of equations that goes into that design. Every one of them asks for 4,000. So your company is going to go jackhammer that deck and then pay to build a new deck. Okay, this is a very high liability profession we are in. All right. This is in addition to the human lives. I'm just talking about economy here, but also the liability and responsibility comes if, God forbid, something fails and then somebody dies. Okay, this is the high liability. All right. So this is a compression test. If we done the lab in person, we would have every group would have broke 2 of those. Okay. Now, the other thing is the dial here. Somebody could say, what is that dial for? Remember, let me skip and I'll come back to that. Remember, we're ultimately going to come to the stress strain curve for concrete. So this is the stress and this is the strain. All right?
Okay,
so
look. Here we go. I'm going to share my screen.
Actually, let me come back to this when I get to the diagram. I'll come back to that. So when we break the cylinder, this is how it's going to do. Look at the cracks. This is a good break. This is a good break because you can see the break coming from here to there all the way through. Sometimes, if it's not a good specimen, it will chip at the top. It will chip at the top, and the machine will stop. That's it. It's failure. But is that a good specimen? No. You want a specimen that's going to crack from here all the way down. That will tell us that the axial load that was applied was concentric or eccentric. That means no eccentricity in there. It was applied exactly through the centroid. Okay? And then look at this something here. What is this piece? This is a piece of rubber. Very strong rubber. And then look at the head. It swivels. It swivels. and then rubber piece. Why? Because we want to minimize the eccentricity. We don't want this machine to push on this cylinder at the corner. No, we want it to adjust to itself over that rubber, so it can minimize the eccentricity. All right. So that's good. Now we get to the stress strain curve. So again, I hope you've seen that in materials lab, and I'm sure you did. So stress strain curve for concrete, this is how it is. We go to strain versus distress. All right, let's talk about the stress first. We already said that stress equal force over area. Now, as you apply this force is gonna apply gradual. You're gonna start from zero and gonna start pushing down slowly, right? So the force is increased, is being increased. So when I put the cylinder, my force is zero. I have a little force. I take that force divided by the area. It gives me a stress here. The force is increasing. I take that force divided by the same area, because the area of the cylinder is not changing, pi r squared. Higher force is going to give me higher stress. Higher force, higher stress. Higher force, higher stress. That's how I get that. Right? The stress is going up. How do I get the strain? How do I get the strain? Again, strength of material. How did we define strain? The strain was defined as the change of length, the change in length per length. Meaning this, the cylinder initially is 12 inches high. When you press it down, you're not going to see it in your naked eye. You're not going to see it in your naked eye. But what's going to measure that distance is this dial. And then, of course, we have even more accurate with the digitals, right? But let's see the dial. So as you compress, let's say if you started from zero, you press a small force, this went down. That amount that this cylinder went down divided by 12 is your strain. Then the amount is going to go down further. The new amount divided again by 12 is the strain. Change in length per length. Okay.
So it's the total elongation versus the original elongation, I think?
Yes. It's the total divided by the original. Okay. So once you do that, then you're going to get these points. Okay, as the load is going up, the strain is going up. Stress goes up, strain goes up. See that? Let's look at this graph here. Let's look at the highest one. So stress goes up, this is the strain. Stress goes up, this is the strain. Stress goes up, this is the strain. See that? And then so forth. And then until what happened? The concrete, it crushes right there. See, this is a crushing of that. This is a crushing of those cylinders. That's it, it fails. So that's the stress strain curve. So look at this guy, the top one, the green. It reached 6,000. So look at this, 6 KSI. Because it's KSI, see the stress is KSI. The strain is really no unit. Why? Because it's inch per inch or centimeters per centimeter. So it's unitless. But sometimes you see it inch per inch, but it doesn't have a unit. So that's why, so this one is 6 KSI or 6,000 PSI. The second one is 5 KSI. The one we keep talking about is 4. This is our mix right here. So 4 KSI or 4,000 PSI. All right? Now, very interesting. Look at the peak of these curves. Again, guys, this course we're gonna be very thorough, trust me. And you're gonna know the answer to everything, why it happens like that, instead of just blowing through it. And that's why I'm spending time. Although you're supposed to know that, but I need you to remember those. It's important. Look at this curve. Look at the peak of all of them. This guy. The peak happens almost at the same point. See that? At what? 0.002. And then next graph is going to show us that. Let me see. See that? We'll talk about that. The peak happens at 0.002. Why is that? We don't know. It's a material property. This nature of this material, it gives us that. And you know, when I did my PhD at UCI, I broke over 100 columns, different sizes of concrete columns. Cylinders, I don't know how many cylinders I broke. Believe it or not, every single cylinder I broke, over 100. This was correct. This was a true statement, 0.002. Amazing. Amazing. I mean, how this number comes out is amazing. And then you will see, the reason I'm covering this in detail, we're going to use this when we start deriving the equations. We're going to derive the equations of design. And you will see some of them comes from here. And it has to. Why? Because we don't know you will see the mechanics of the problem. We're not going to be able to solve it by just mechanics. We need some experimental numbers to reflect the characteristic of this material. Where is that going to come from? From the stress strain curve. Okay, we'll come back to that. I'll show you. So let's go back to this. So this is that. So let's go on the next slide. Is going to show us. It says the relationship between stress and strain is roughly linear at stresses level equal to about 1/3 of 1 or 1/2. What he's saying here is, look at this. This is the top, right? So this is 6. So 1/2 of it is 3. Look from 3 to 0. That line is almost a straight line. That line is almost a straight line. That's why we call it linear material up to this point. I know you heard about linear, non-linear, elastic, inelastic, plastic, all these. So I'm going to try to cover as much as I can from those. The first one is, I want to tell you, is the linear versus non-linear. So this is, let's take the highest one. When you apply the load to here, it's going linear almost up to here. See that? After that, it's starting to curve. Let me see if they have a tangent. Yeah, right there. It's showing that up to almost half. Let me see if there's a no. See that? So let's take it to the 3 as a half. Now, as you're loading that cylinder, and then you're applying the load and you get to this point, if you lift that load, you stop the machine, guess what's going to happen? This point is going to go back to 0. That means the cylinder is going to, in theory, rebound. We call that elastic, and we'll cover it more in steel when we do that. So it's a linear elastic, okay? But so let's just do the linear now. And then as you go up, it's going to go non-linear. Okay, so non-linear. So in theory, the concrete is really non-linear material. It's not a linear. Look what happens to it. It goes that way. So that means when you're here, if you release your load, you're not going back. You're not going back. Okay, you're not going back to that. It might rebound a little bit, but it's not going to go back. Okay? So, okay, we were here. It says 1/2 to 1/3 to you ultimately be between the strains, roughly linear, I mean straight line, up to 1/3 to 1/2 of the ultimate strength. At the ultimate is right here. Beyond this point or this range, the relation is a nonlinear material. See that? It comes nonlinear. Again, when we design, when we do derivations, we're going to come back here. Okay, regardless of compressive strength, all concrete reaches their maximum strength at a strain of 0.002. See that? Right there. And I told you, I seen it in my lab. That is always the case. Material characteristic. It reaches its ultimate. Look at this guy here. The 3000, right there. The 4000, they're all the same, 0.002. And then, I think we're going to see that later. Yeah, we're going to see more stuff. All right, concrete does not have a well-defined yield point. See that? That's what the yield is. The yield is, and it's going to be much clearer in steel. The yield is, as I mentioned before, if I stop my load here and then I lift the load, it's going to go back. If I stop my load here and then I lift it, it's not going to go back. At some point, when When the curve doesn't go back, that means that material has yielded. That yielded. It's not going back. We'll talk more about it in steel. It's much clearer in steel than concrete. So please give me a little time. Okay, so the concrete does not have a well-defined yield point, but the steel does. Steel does. Ultimate strength. So look at this. Look where the concrete is breaking. These first two, they broke at roughly this point, or the green and that roughly broke at this point, 0.003 strength. But look at the lower ones, the 4,000, 3,000, they broke at 0.004. So the ultimate strain is achieved is on the order of 0.003 to 0.004. You can see that. Lower strength concrete achieve higher ultimate strain than does the lower strength. Okay. Now, it doesn't mention it here. So you will see in design, we are going to take this point, and I will remind you when we get there. We're going to take that the concrete will break at 0.003. The rest of this, we're going to have it as factor of safety. Without this number, guys, we cannot derive the equations to design any concrete members. And I will remind you of that. Because I remember we will derive all the equations from mechanics. Then I need this number here to plug it in order to solve the problem. Without that, you cannot solve the problem. So where did this number come from? Experimental. See that? So a lot of time in engineering, to solve it, you need analytical and experimental. Analytical is when you follow the mechanics of these things. How does this perform? And the experiment is what you do in that. That's why in steel design, in concrete, 99% of the equations I will derive for you. In steel 455, a lot of the equations are very long, and they are not derived. They come from experimental works. It's just because of the nature of the material. Okay? We'll talk about that. All right. So this is the stuff, and again, we'll come back to that. Static modulus of elasticity. Okay, modulus of elasticity. You've seen it in structural analysis when we calculated deflections. You've seen it in strength of material or deformable bodies, and now we're gonna need it in concrete. So it's called static modulus of elasticity versus dynamic. Okay, we were doing static. Concrete does not have a single modulus of elasticity. Okay, it doesn't. That means it varies. Steel, on the other hand, it does. Steel, the modulus of elasticity of steel is 29,000 KSI. Always the case, constant. 29 million PSI or 29,000 KSI. But the concrete does not. Let me jump here. Look at the formula for concrete. The modulus of elasticity is 57,000 square root of F prime C, meaning that it depends on the value of F prime C, you calculate AC. But the steel, both the reinforcing steel and the structural steel, the modulus of elasticity, we call it E sub S, is 29,000 KSI. All right? Now, the particular value varies with the concrete strength, age, type of loading, and so forth. The ACI gives us the equation of this guy here. See that? EC equal 33 WC. What is the WC? That's the density of concrete. The density. So to the power 1.5 square root that. For concrete weighing about 145. Remember I told you earlier 150? This is the density we use in design. So here he's telling us it's really 145. But we use 150 because remember, when you put rebars in there, you're going to displace some of this concrete with steel, with reinforcing steel. And the density of steel, and write it down, is 490 pounds per cubic feet. So we take the same box of the basketball, we melt a steel and fill it with melted steel. Weigh it, it weighs 490 pounds, guys. Can you imagine that? The concrete weighted 150, the other one is 490. So if you insert a rod in the concrete, that's going to displace a volume of concrete. But the volume of steel is much heavier than the concrete. So, but the amount is smaller, right? I mean, it's a half-inch bar or a 3/4 inch bar, whatever. So that's why they count on one. So if you put 145 here to the power 1.5, you're going to come up with 57,000. But, you know, you're very seldom going to see this. This is what you're going to see. All right? So the EC is equal to that. And we're going to use it a lot. EC comes into account a lot when you are doing deflection calculation. Okay? Now, for high strength concrete greater than 6,000, there's the equation. We're not going to do that. We're going to cover only the normal strength, not high strength. But if you're dealing with high, this is the equation to get that. Dynamic modulus is about 20 to 40% higher than the static modulus. Again, we don't deal with that, but just to give you an idea. So all we need to do modulus is this guy right here, 57,000, and that's where it came from. Okay, next characteristic of concrete is Poisson's ratio. Again, you've seen those, hopefully you heard about those. Poisson's ratio, what happened when we press the cylinder down? It goes down, but we don't see it in naked eye, but it also goes out. Visualize that. It goes down and it goes out. Very small, of course. How do we measure that? By Poisson's ratio. Poisson's ratio is about 0.11 for high strength concrete, 0.21 for low strength. For average value is about 0.16. Okay, so this is what Poisson's ratio is all about. We're going to see that a little bit further down, but not a lot. But you will see where it plays a role. Okay, shrinkage.
Can you go back that page?
Yes. So shrinkage, of course, we said that earlier. If the water dries or you don't have enough water, the concrete is going to shrink. And when it shrinks, it cracks.
You could move on.
You okay now?
Yeah, I got it.
Okay. Workable concrete requires more water than is necessary to fully hydrate the cement. See that? Usually you need more water to put in. Requires more water than is needed to fully hydrate. As water cures, water not used in hydration begins to evaporate. See that? I mentioned that. The water, if you put too much water, the hydration process is going to take only so much. What's going to happen to the rest? It's going to evaporate, the volume is going to be reduced. Okay? So as concrete cures, that means it doesn't need any more water. Water not used in the... I'm sorry?
Can you...
I'm sorry? Can you mute your phones, please? Please mute your phones or computers. All right, so as concrete cures, water not used in hydration begins to evaporate, right? So the surplus water is going to leave. The effect of evaporation water is shrinkage and cracking of the concrete. Why? The volume is reduced. It's going to try to shrink it down, and as a result, cracks. Shrinkage occurs for many years, but about 90% occurs within the first year. See that? The shrinkage continues for years, but the majority of it happens in the first year. The amount of moisture lost depends on the distance from the point in the concrete to the surface. What it means is that if you have a drop of water in the middle of the beam, in the center of the beam, for that drop of water to evaporate, is going to travel all the way to the top or to the bottom. But if that drop of water is close to the surface, it's going to evaporate much quicker. That's what this means. The amount of moisture lost depends on the distance from the point on the concrete to the surface. And then members with large surface area have a higher rate of shrinkage, right? You have large surface area, you have large exposure to the sun, shrinkage, evaporation is going to be quicker, shrinkage is going to be faster. The amount of shrinkage depends on exposure of the member. You know, how exposed to the sun and to the air the member is. Okay, shrinkage, keep mixing water to a minimum. Keep mixing water to a minimum. Don't add too much water. Cure thoroughly. Place concrete in small sections in order to manage shrinkage. That's what you need to do. Keep the amount of water minimum. Cure it well. Place concrete in small sections. Don't place too big of sections. Use construction joints, like I mentioned. Use a straight joint, then continue next morning. Use shrinkage reinforcement. Sometimes we put rebars in there so we can control the shrinkage. We'll talk about that. Use dense, non-porous aggregate. Use the dense, non-porous because if the aggregate is porous, it's gonna suck some of that water. So the cement is gonna lose that. But if it's dense, it's not gonna take any water. The water is gonna be used for hydration. Creep. You know, when Halloween you say something is creeping at you, that means slow motion. Slow motion. So creep is deformation under sustained load. It means the load is there all the time. The concrete will start to creep slowly over the years. Creep is also called plastic flow. Very slow. Creep deformations may be 2 to 3 times as large as instantaneous deformation. Instantaneous deformation, that means what happens right now. And then the creeps happen over the years. That's why sometimes you drive on a street and you see a buckle in the road. That's as a result of creep over the years. It keeps creeping and then it buckles. 75% of creep occurs during the first year. See that? So that happens. The amount of creep is dependent on, let me see how far we're going. Okay. Yeah, we're going to stop here. Let me stop here because I know you have other classes. So, all right. Any questions? Any questions on that? Sorry, I didn't take attendance, but let me see. I can tell from the list here. Yeah, so please make sure you attend the class, okay? All right. Any questions? Anybody have any questions? All right. So just a quick reminder, make sure you work on your groups. Make sure you get in a group with your lab. And then today in tonight's lab, hopefully I will get the Friday lab. I think the first one, we have all the groups assigned already. I would like to assign the Thursday group today. And then also, of course, the Saturday group, we assign them on Saturday. So start thinking about that and then we'll do. Any questions? If not, then we're done for tonight, and I'll see some of you at 7.
Thank you, Professor.
You're welcome. Thank you. Bye-bye.